Hello, hello, hello. Can I hear myself? Yes, I can. Okay, cool. That sounds alright, actually. Um, what was I doing? So, yesterday I was reading without focusing, basically. So, we're gonna resolve that by reading through the page again and coming to terms with what it's saying. And a few more improvements have actually. I tried to connect my I've got like a Surface Book 2 tablet thing here, and I tried to connect this computer to my Surface so I could like see the screen. But actually slowed down the Surface Book 2 pen and paper, or so I thought. And then I realized that it was actually because the other whiteboard had got so big that it's actually slowing down the Surface. So there's a word of advice is don't write loads of notes at different sizes because it really strains whiteboard. Anyway, the solution was to just put these kind of partitions around the thing. So hopefully I don't muck it up this time, but I probably will. Good. Okay, so yeah, where were we? Yes, we started inner product spaces. So let's read from there and work our way through it. Actually, I just need to make sure I can see what I'm doing here as well. Bear with me. How do I see myself streaming, I wonder? Let's click that one. Oh, let me do that. Sorry about this. Oh, it's going very well. Here we go. Alright, cool. Um, and can I chat? Yes, I can. Alright, cool. Let's do that then. Yeah, and you can see me. Alright, good. So, can I actually see the words on the screen? Questionable, questionable. Very difficult. I can't do anything about that. Oh, actually, that's a lie. Um, no, it's not a lie. Damn, yeah. So the words on the screen are a bit difficult, but I'll read them anyway. So, inner product spaces. The matrix and function examples must have convinced you that we can have a vector space with no preassigned definition of length or direction for the elements. However, we can make up quantities that have the same properties that the lengths and angles do in the case of arrows. The first step is to define a sensible analog of the dot product. For in the case of arrows from the dot product, we can read off the length of, say, A as square root of a dot product of A, and the cosine of the angle between two vectors as A dot product B, A the dot product of A and B divided by the magnitude of A and B. Now you might rightfully object, how can you use the dot product to define the length and angles if the dot product itself requires knowledge of the lengths and angles? Okay, well we figured this out because, or we read it because the this can also be written of the as the sum of products uh, divided the sum of it's just the sum of products, isn't it? Can't remember. Recall that the dot product has a second um, equivalent expression in terms of the components. Yes, the sum of products. So they're just saying that um, the dot product of A and B divided by the magnitude of A times the magnitude of B. Ah, is that right? Yes. Wow. Okay. Cool. Is equivalent to saying the the sum of A. What is it saying here? sum of each component in the vector. So in this case, they're defining uh, it as a three-dimensional vector. Yeah, and so they're just adding um, my apologies. Sorry. They're just adding each one like this. Well, I don't know why that was so difficult for me to write that. That's not a C, that's a Z. Oh gosh. So they're saying those are equivalent, and so we can make that same assumption that we had before with linear dependence and independence. Our goal is to define a similar formula for the general case where we do have the notion of components in a basis. To this end, we recall the main features of the above dot product. So there is a symmetry. It doesn't matter which way you multiply these, they still come out the same. Um, the dot product of A's is greater than or equal to 0 if and only if A is equal to 0. Let me just reflect on this one. Uh, the dot product of A is greater than or equal to 0, 0 if and only if A equals 0. Oh yeah, how did these ifs work again? So let me just pull up the sheet that we were working on before. So it says when you say P if Q, it means that Q is true, then P is also true. So 0 is true if A is also true. However, P could still be true even if Q is false. It's actually saying 0 is true if A is also true. Um, so let's take the following equation. So we've got A dot, or let's call dot product of A. Well, can we do AA, something like that, is greater than or equal to 0 if A is equal to 0. Um, in this case, the book states it is positive semi-definiteness. What does that mean? It's hard wording for me to follow. I have to say, the whole book so far has been like this, but I think it's just me maybe. I'm just not used to these sorts of ways of talking. The equation you've written seems to be describing the properties of the dot product in the context of vectors, although there seems to be a minor error in your statement. Yeah, that's. Let me just make sure I'll actually put that correct. So the dot product of A is greater than or equal to 0 if A equals 0. No. Ha. Whoops. Okay, let's try that again. 0 if A equals 0. Here we go. The phrase positive semi-definite is generally used to describe matrices or functions that, informally speaking, never output negative values. In the context of vectors and the dot product, when we say the dot product of a vector with itself denoted as .aa or simply a.a is positive semi-definite, we mean that this quantity is always greater than or equal to 0. That's the positive part. And it equals 0 if and only if, that's the semi-definite part, the vector is the 0 vector. there's a lot said there. We mean that this quantity is always greater than or equal to 0. Now, so I assume, let me just think about dot product for a second. Coming from game development here, I think we've got um, this is a normal, let's say. This is our axis, right? And this is the origin, let's say. And this is a normal. And when you take a dot product, you measure the, whoa, what did I just do then? We measure the vector's dot product with the normal vector. And so this is the dot product of v dot n, right? And if that equals 0, which e.g. is this is 0, then there should be white returned, or at least that we have the notion of it should be fully reflective into your face. On the other hand, if it's less than 0, then we're somewhere over here, and so you can start to return more of the actual color that sits behind that pixel that you're going to either turn white or whatever. So it takes a scalar of the color that you're reflecting back. And so this is the negative, and this would be the positive. So over here, well, just this again. Over here, so we've got v prime here. Then yeah, this is positive, and actually I should really draw positive. So keeping this in mind, quite it's nice now it's all smooth. Keeping that in mind, this says it says in the context of vectors and the dot product, when we say the dot product of a vector with itself, denoted as .aa or simply aa, is positive semi-definite, we mean that this quantity is always greater than or equal to 0. So it's always over here. Oh, that's not the right color. Try that. It's always over here. Actually, even better. Let's do that. That's the positive part, and it equals 0 if and only if, that's the semi-definite part, the vector is the 0 vector. Interesting. And I wonder then, let's ask, in the case of um, a normal vector, its dot product and how reflective something should be when rendering games, is the null vector the normal vector? In a way. uh, Yeah, so the null vector, also known as the zero vector, is a vector in a given vector space that contains only 0 values. We know this. On the context of surface normals and computer graphics, the null vector is generally not useful because it doesn't have a direction. It's not pointing anywhere. So while the null vector is a kind of vector, it's not typically used as a normal vector. When it comes to rendering and lighting dot product, well, I suppose it kind of didn't understand what I was saying. Let me just try this again. I don't mean for you to take this explicitly. I'm simply trying to analog uh, the understanding from the book with something I already know. For example, I drew a vector coming in from the left, diagonally down, a vector coming out the other side at a right angle to the original vector, and then drew a normal which was perpendicular to an axis line. I then highlighted the right hand side as the semi, what did it say again? Semi something? Semi-definiteness. Semi-definiteness. And noted that in this drawing we could assume that the normal vector, that perpendicular one, would count as the null vector, even though just as a helper rather than explicitly true. Just because I want GPT to kind of analyze the fact that I'm actually just trying to come up with some anecdote? No, something like that. Let's see if we get it. Otherwise, we'll just carry on because I think it's right anyway. Let's read this. So, in the context of the dot product for a vector with itself is essentially the square of the magnitude or length of that vector. For any vector, this value will be 0 only if the vector is vector with no magnitude or direction. It's important to note that a zero vector and a normal vector are different things, yeah, we know, as a normal vector is typically defined with respect to a surface and zero vector. As for the concept of symmetry, it is less about normal vectors or null vectors and more about the properties of the dot product operation itself. The dot product of any vector with itself will always be non-negative, greater than or equal to 0, making it positive semi-definite. Okay, so where does the term come from? It's quite explicit and nuanced. Perhaps talk about it in terms of its etymology. I always like doing this because then I can get the kind of Greek understanding of the phrase, and then it kind of leads to some simplicity in understanding it. The term positive semi-definite comes from the field of linear algebra and is used to describe certain kinds of matrices and quadratic forms. Here's a bit of context on the terminology. Positive, in the context of matrices and quadratic forms, positive usually refers to the fact that the entity produces only positive results when applied to non-zero vectors. In the case of a positive semi-definite entity, this is generalized to non-negative results, including 0. Semi-definite, the prefix semi means half or partially. In the context of matrices, a definite matrix is one that produces either strictly positive or strictly negative results when applied to non-zero vectors, depending on whether it is positive definite or negative definite. By calling a matrix semi-definite, we're saying that it is partially or halfway to being a definite matrix. Specifically, a positive semi-definite matrix can produce positive results or 0, but not negative results. The term is thus a very precise way of describing a certain set of properties that a matrix or quadratic form can have. It's used in various fields of mathematics, physics, and engineering, particularly when quadratic equation. It's too wordy. Okay, fine, we'll just live with it. So this next one says the the a the dot product of A and the coefficient scalar of the product of the coefficient scalar and B plus the product of the coefficient scalar and C is equal to the addition of those things times another. Right, let me write this out because this is not so clear. And I think I'll just scrub this one out as well. So it says the dot product of the coefficient scalar multiplied by the vector, it's got these little signs on it, plus the coefficient of the product of the coefficient C and the C vector is equal to the coefficient of b multiplied by the a vector. Ooh, okay. Um, a dot product of b as well. Okay, interesting. Plus c a c. Okay, so let's just have a look at this. How is it that how is it that this is equal here? Well, okay, so we are literally just multiplying this out. So that makes sense. That's this part. Um, because it's gonna be. Oh, that no, that is interesting. I'm not sure. Okay, so it's not just a given. And then you've got this C part over here, which is kind of the same thing, right? But then I need to prove to myself this is right. So if I were to go, um, it's saying that if I were to multiply this out, we've got A, um, B, B plus A, C, C. That's how that works. Um, and so because these can go in any way, shape, or form. Wait, oi, oi, oi. Why is that then? I can see where they're coming from. Like these things feel like that's where they're coming from. But to get B, um, it's very hot in here. I have to say. Where's the temperature? Let me just see. I'm struggling to focus here. What is the temperature? Oh, okay, 23 and a half. Okay, wow. Just trying. I'm trying to find how these link together at the moment. So sorry, it might take a little while. I'm a bit slow at this sort of thing. I don't do this stuff enough. So somehow it's multiplied with a, but they've taken the coefficients away from the because it doesn't matter in what order you do that. Like what's interesting is that plus symbol. So basically it's just moved. But the thing is, this is the dot product here. So they're saying that it's the same as the dot product of a. And this is what's happened here, right? I see. Um, yeah, we've got the same now. I understand that. So what we should do to analyze this then is to actually do the dot products in that above some form. I think that will help me out here understand this. So if I were to do the dot product of A and B would be because this is not actually a multiplication. This is the dot product of. I'm an idiot. I'm an idiot. Yeah, yeah. Okay. Well, that makes sense then. I always think the dot is the multiplication, but it's not. It's actually the dot product, which makes sense, right? So if you're going to do so yeah, if you're going to do this, you can do a dot product of b, and then you can just scale this by the b. Yeah, exactly. Yeah, this one here. Yeah, cool. And so on and so forth. Good. Okay, understood that. Um, it's linearity. The linearity of the dot product is illustrated in figure 1.2. So it's saying that, let's see if I can get this a little bit bigger for us. Pop this in here. No. Can I undo that? I can't undo that. Great. Yeah, okay, so it says that the linearity of the dot product is illustrated in figure 1.2. Alright, so let's do a bit of highlighting here. It's got this J, K, and L components of the vector. So, of course, we've got our A, coefficient A. Let's do this. Whoops. We've got A vector J plus beta. I don't know why they've done it like this. We're going to just redraw it with the above things, but okay. Is equal to, or actually more so that, let me just move this over. This is saying that the A multiplied by the vector component J plus yeah, okay, well, this is pointless, right? Beta vector K is equal to that, of course. And then it's saying it's because you've got like this theta here. And is this a comma? No, I think that's something else. Is that a P? I'm not sure what that says. But it's also saying that a j plus sorry, aj pj, I see. It's saying that pj plus um, hmm. Geometrical proof that the dot product obeys axiom 3 for an inner product. The axiom requires that the projections obey pk plus pj equals pk. pjk. Where is pjk? So you've got this plus this equals this. Well, that makes sense. But it's geometric proof because we saying here? Oh, always difficult this stuff. For me, I'm an absolute idiot. So um, I know what it's trying to get at, but I'm trying to unravel it to explain it, I suppose, to myself, to you, the viewer, to me, the viewer, when I come back to this at some point. I understand what it's saying, which is the most annoying part. I'm just trying to understand why it's got so many other bits and bobs here to explain it. It says that the linearity of the dot product is illustrated in figure 1.2. We want to invent a generalization called the inner product or scalar product between any two vectors, v and w. Let's let this sink in a bit more. How is that proof that the dot product obeys axiom 3? And axiom 3 was... doesn't say actually. Definition 5, 4, 3. The set of vectors is said to be linearly independent if only such linear relation as equational is trivial one with all. So it's not linear, we say that they're linearly dependent. And this one says our goal is, yeah, we want to invent the linearity of the dot product is illustrated in figure 1.2. Hmm. Geometrical proof that the dot product obeys axiom 3 for an inner product. Right. What's the difference between a dot product and an inner product? I thought they were the same thing. Vector spaces, the term dot product and inner are often used interchangeably, but they have different meanings depending on the context. Dot product, the dot product is a specific kind of inner product that is defined in real or complex Euclidean space. It takes two vectors and returns a scalar. In 3 dimensions, for example, the dot product of vectors is calculated as inner product. The inner product is a more general concept that applies to more abstract vector spaces, not just the Euclidean space. It is a binary operation that combines two vectors to form a scalar. The inner product must satisfy several properties including commutativity, linearity, and a positive definite property. In the context of Euclidean space, every dot product is an inner product. However, in more abstract settings, inner products can be defined in ways that go beyond the standard dot product. For example, in the space of continuous functions, the inner product of two functions, f of x and g of x, might be defined as the integral of f of x, g of x, d of x over a certain interval. So in short, all dot products are inner products, but not all inner products are dot products. Space of continuous functions, the inner product of two functions might be defined as the integral. Let's see if GPT knows how to help here. So if I say um, in the Principles of Quantum Mechanics by R. Shankar, there is a figure 1.2 which is a geometrical proof that the dot product obeys axiom II for an inner product. The axiom requires that the projections obey P sub k plus P sub j equals P sub jk. Um, it states that it's point 3 a how do you do a dot product thing? See if I can copy it out. Yeah, let's get that little dot there. A dot b plus c equals b plus c linearity is illustrated by the figure 1.2. With this in mind, I'm struggling to see how see fully what the book is trying to tell me. Any ideas? This is what happens here. The dot product is linear in each of its arguments. That is, for any vectors a, b, and c, and any scalars b and c, the following is true. The vector projection of a onto b, denoted p sub b, represents the component of a in the direction of b. Similarly, the projection of a onto c is p sub c. The projection of a onto the vector b plus c, a linear combination of b and c, is p sub. Shankar's axiom 3 states that the projection should obey the rule pk plus pj equals. In the context of figure 1.2, this would translate to. So sorry, the figure is a geometric illustration of how the dot product and hence projections of vectors. No. It might help to think about each term of the equation separately and how they represented geometrically. Remember that dot product of. No. Can you try again to explain this to me? It hasn't sunk in at all. The dot product or inner product is a way to multiply two vectors together that gives you a scalar, just a regular number. It is linear in the sense that when you multiply a vector by a scalar and then take the dot product, you can pull that scalar out in front. It is linear in the sense that when you multiply a vector by a scalar and then take the dot product, you can pull that scalar out in front. This is what a dot product of b equals this is saying. Here, a, b, and c are vectors and b and c are scalars. So let's try to illustrate this with an example. Say we have vector a equals 1, 2. Alright, let's do this. We have vector a is 1, 2, 1, 2, 1, 2. Vector a is 1, 2. Vector b, let's say, is 3, 4. try this a bit smaller. Okay. Can you actually add just graphs? Just for future reference? No, you can't. Whoops. I was interested to know if this would... Oh, it doesn't seem to work. That? Oh, it just kind of adds it. Oh, that's not very helpful, is it? Why would it do that? If I wanna... Okay, fine. Not a fan of that at all, I have to say. Wow. That is so not good. Okay. So it says vector A, 1, 2. Okay. 1, 2. So this is vector A. And this is vector B, 3, 4, 3, 4. And then vector C, 5, 6. 5, 6. Oh wow, that's really thick. Okay, cool. Scalar B equals 2 and scalar C equals 3. First, let's calculate the left-hand side of the equation. A dot product of B plus C. We first need to compute B plus C. We multiply vector B by scalar B and vector C by scalar C, and then add these two vectors together. So I would need an even bigger diagram here, I see. I can't do it on this page, I think. Let's see if I can move this along to our second section instead. Let me just do that 1 sec. Whoops. How do I grab stuff like that? Aha. I'm going to move that over to here. Try again. Move that over to here. And then I'm gonna have to move that down to give me more space. Like that. And now let's add, was there a scalar of 3? God, okay, 12. 7, 8, 9, 10, 11, 12. You know what? Maybe instead of doing this, let me just do this in Desmos. I think that'll be easier. That you have to hold Control to do that. Okay, cool. Delete. Whoops! Do me to get rid of my. Oh, I can't undo now. Yeah, undo doesn't work. All right. Well, that's dangerous. Let me close Microsoft Whiteboard and then just try again. And then I'm going to load Desmos. Alright, graphing calculator. And then we're going to go x equals 1, y equals 2. Oh, you can't do that. I need to do a graph instead, no table, that's the one. 1, 2, 3, 4, 5, 6. Can I do lines? No, I guess I can't. So that's not it. How do you draw lines in Desmos? Let's have a little look.
During our class chat, I noticed a lot of you said you didn't really even know how to use Desmos to do slide 9. So since our homework has another option to kind of play with this activity a little bit more, I thought it would be helpful to kind of talk through just how to use Desmos. So if you notice, there's 4 stars here, and a lot of you had success catching maybe 1 or 2 stars, but I only saw like 3 of you catch all 4 stars. And a lot of you were complaining about not being able to stop your line, so you wanted a line segment instead of a line. So I'm going to show you how to do a line segment on Desmos. So I'm going to type in an equation for a line. Let's do like y equals x plus 5. Let's go a little bit lower because I want the marble to hit that. So if I do y equals x plus 4, that gives us a full line. But if you notice, it's impossible now to hit these bottom 2 stars. So what I want to do is I want to cut off my line at a certain point. And the way you're going to do that is you're going to do a curly bracket, and then you can either restrict the x values or the y values. I noticed that I kind of want my marbles to stop sliding at x equals 5 and at x equals 11. So I'm going to make an inequality that restricts x to those values.
God, I
And
can't
if you
love to do
notice now
that.
when I launch, it slides off. So I would probably have to shorten this line even more. Ooh, let's do like 10. And if you notice, if I launch now, some of
Sure there's a better way of doing that. Okay. Um, Aha. Interesting, interesting. I didn't even know it had that. So, is it? No, okay. This one? Nope. Fine. How do you do that then? I'm learning now. So it's saying table. Ah. Ah. Uh, let's try this again. So it says 1, 2. Don't think it's letting me do it actually. Ah, here we go. Lines. Alright, cool. So how does this work then? Plus table 1, 2. I guess I want 0, 0 to 1, 2. And I want that to be drawing lines. Ah, cool. Alright, cool. Drag. Nice. Let's turn that dragging off, because that might get a little bit annoying. And I wonder then how to add another line then. Let's see. 0, 0, 3, 4. Ah! So I can actually add, right, I've got it now. Okay. Very nice. If I do another table then, I'll do 3 and 4. I won't. I'll do 0 and 0, 3 and 4. And I'll make that a line as well. And then I'll add another one. 5, 0, 0, 5 and 6. Sayings, that one. Line, done. Okay, cool. We've got our lines. And then what did it say? It said, no, now I need a scalar. So can we make this uh I guess yeah, I guess we let's just draw it. Okay, so first need to compute BB plus CC. We multiply vector B. Can I add a note or something? Plus note. Okay. So this is vector A, vector B. Oh, ha. Okay, sorry. A, B, and then C. Okay, and then we're going to yeah, add. We multiply vector B by the scalar B. Okay, so the scalar B. Let's go expression. We'll put that at the top. B equals 2 and C equals 3. Good. Okay. A equals x3. I bet there is a way of making it equal that as well. So how to set a variable equal to a table output in Desmos. You can make a variable in your function by adding a little to your script. Well, you know what? You know what I could do? I could just like take a snippet of this now, couldn't I? Yeah, let's do that. Let's just do that. Okay. I'll learn how to use this one day, but today is not that day. So zoom back into 2, paste that in. Hopefully, I can now start playing with this properly. Okay, right. Let's try this again. So b plus c, we multiply vector b by scalar b and vector c by scalar c. So this is vector b multiplied. Let's do this. A, b, c. We multiply vector b by scalar b. B equals 2, c equals 3. B by 2. This is going to be about there kind of thing. And then c is going to be 3. It's going to be about there. Okay. And then add these two vectors together. So if I were to do that, probably be about, well, let's see, it's going to add that to that, so it's going to be about there. And then add these together. So it's going to be BB equals 2, I see, 6, 8, I see. I think it's given us help here. Yeah, it is, yeah, okay, let's do this properly then. So B is 2 times 3, 6, 8. 6, 6, 8. Awesome. Thank you. Thank you. GPT C3 is 15, 18. 15, 18. Let's see if we can do this properly. Can I have purple, please? Nice. And then B plus C is 21, 26. 21, 26 here. Let's try it again. In fact, let's do this a different color. Let's do this blue. Okay. Um, we then need to take the dot product of A and this new vector B. The dot product of A against that equals 1 to 21, 6 equals 121 plus 226 equals 73. Now let's calculate the right-hand side of the equation. We first need to compute AB and AC. 24, 11. Sorry. 11 and 17. We then multiply these results by scalars B and C respectively and add them. 20 plus 51 equals 73. They're equivalent. Okay. As you can see, the left-hand side, A B equals the right-hand side. So the equation holds and the dot product is indeed linear. In terms of geometrical, that was a complete waste of time then because it actually tells us here. In terms of geometric, I think I'm going high or something here, bear with me. My sugars, I'm diabetic, you see. Oh yeah, I'm starting to get a little bit high. Let me get my injection out here. Um, okay, fine. So in terms of geometrical interpretation, the dot product measures the length of the projection of one vector onto another. The figure from the book should be showing this property in a visual way, illustrating that the projection of vector A onto the vector created by the linear combination of B and C is equal to the sum of projections of A onto B and A onto C. So let me see here. I wonder, I think maybe I'm starting to understand this now. Maybe it's just saying that simply because um, this projection and this projection uh, yes, it is. That's exactly what it's saying. Ah, I see. So the dotted lines in the figure 1.2 are simply projections from the addition of the vectors onto the below lines, which are the inner products, which are representative of the single number, the inner product. Yes, that's correct. Okay, the dotted lines represent the projections of the vector A onto the other vectors. The length of these projections is what's being calculated when you take the dot product. The figure is showing that the length of projections of A onto the linear combination B, C is the same as the sum of the lengths of the... Yes, I've got it. Okay, cool. Right, we understand now. Oh my goodness, I'm so slow. Great though, we're getting somewhere. Right, okay, next one then. The way it says, let me just move along. It says, we want to invent a generalization called the inner product or scalar product between any two vectors. We denote it by the symbol VW. So, I'm understanding here that the inner product is the inner product of it is VW. Let me try this again. We want to invent a generalization called. Whoa, there's massive static coming off my table here at the moment. We want to invent a generalization called the inner product or scalar product between any two vectors. We denote it by the symbol inner product or scalar product. So let's redo this. Inner product or scalar product. Inner product or scalar product. And we denote it like that. Okay. It is once again a number, generally complex, dependent on the two vectors. We demand that it obey the following axioms. The inner product of VW is exactly the same as W and V. Skew symmetry. The inner product of V on V greater than or equal to 0. 0 if V is equal to, if and only if V is equal to 0, positive semi-definiteness, and that you can multiply the scalar coefficients by the same thing to get the same thing. And that's proven by that projection. Ah, okay, I see. Um, Loosely see. I'm not feeling the strings pulling everything, but it's enough for me to get on to the next part, I think. A vector space with an inner product is called an inner product space. Notice that we have not yet given an explicit rule for actually evaluating the scalar product. We are merely demanding that any rule we come up with must have these properties. With a view to finding such a rule, let us familiarize ourselves with the axioms. The first differs from the corresponding one for the dot product. Oh, excuse me. And makes the inner product sensitive to the order of the two factors. Let me say it. The first differs from the corresponding one for the dot product and makes the inner product sensitive to the order of the two factors, with the two choices leading to complex conjugates. So I've got two words I don't understand here. Um, two words came up in the book for me. Factor, um, factors, and conjugates. The sentence they are used in is as follows. Um, could you help explain to me? Exaplain to me. Oops. Absolutely. Firstly, let's understand what factors mean in this context. In mathematics, factors are numbers, variables, or expressions that are multiplied together to get a product. So in the context of the inner product, the two factors refers to the two vectors or objects that you're applying the inner product operation to. As for complex conjugates, let's consider a complex number. A complex number is a number that can be expressed in the form A plus bi. Let's conjugates. Let's consider a complex number. Um, excuse me. Um, is a number that can be expressed in the form a plus bi, where a and b are real numbers and I is the imaginary unit, which satisfies the equation I squared equals -1. Well, we know that one. The complex conjugate of a complex number is obtained by changing the sign of its imaginary part. So the complex conjugate of the number a plus bi is a negative bi. In the context of the sentence from the book, it is saying that the order of the vectors or factors matters when computing the inner product. In other words, the inner product is not commutative for complex vectors. The inner product of vector A and vector B, denoted AB, is not generally the same as the inner product of B and A. In fact, the two are complex conjugates of each other. This property is not seen in the regular dot product operation with real vectors, which is commutative, i.e. A dot product B equals B dot product of A. This distinction is a key aspect of the inner product operation in the complex vector space, often encountered in quantum mechanics. Oh, fine. So it says notice that we have not yet given an explicit rule for actually evaluating the scalar product. We are merely demanding that any rule we come up with must have these properties. With a view to finding such a rule, let us familiarize ourselves with the axioms. The first differs from the corresponding one for the dot product and makes the inner product sensitive to the order of the two factors. Now this makes sense, with the two choices leading to complex conjugates. In a real vector space, this axiom states the symmetry of the dot product under exchange of the two vectors. For the present, let us note that this axiom ensures that the inner product of V to V is real. The second axiom says that V to V is not just real, but also positive semi-definite, vanishing only if the vector itself does. If we are going to define the length of the vector as the square root of its inner product with itself, as in the dot product, this quantity had better be real and positive for all non-zero vectors. The last axiom expresses the linearity of the inner product when a linear superposition AW plus BZ equals the AW plus BZ appears as the second vector in the scalar product. We have discussed its validity for the arrow cases. I'm so sorry for yawning. Figure 1-2. What if the first factor in the product is a linear superposition, i.e., what is AW plus BZ V? What is this pipe then? Oh, I see. It's the inner product of AW plus BZ and V. This is determined by the first axiom. So let's get to grips with this. I like to write these things out because it makes me think about what it's actually saying. So it's saying that the inner product of AW plus BZ with V. Sorry. Here we are. Is equal to the inner product of V and AW plus BZ by BI. Don't know what that means really. Let me just move this along as well. I don't know what BI is. So therefore it says that A times the inner product of VW plus B times the inner product of, let's see, VZ. Is this inner? Oh yeah, VZ. Okay. Yeah. Inner product of VZ. Um, hang on a second then. Let me rewrite this again. It's saying that A, and this is all in brackets, inner product. I'm gonna have to do that because I'm getting confused with less than or equal to sign here. VW plus B V Z. Okay, it's a bit neater now. So, does this make sense to me? It's saying that we can take the coefficient off, or outside of that. And when you do so, you have to, like an equation, multiply both sides. Because if you're removing this over to here, sorry, it's a bit confusing, over to here, then it's the same plus BZ. Wow, okay. You got W and Z. W and Z are being plussed together, and that's why they remain separate. But then you've got, yeah, because they're either side of this plus. But then it's saying that the inner product of those plus is the same as the inner product of both of them multiplied by A and B. Interesting. How does that? Hmm. Okay, so what's happened here? They've said, given that we have all those rules before, we could say that so this is the symmetry. Um, and this is this um, what's it called? Uh, this is called addition something something. Let me just try and find it. I know, get there soon. This is the uh, commutativity of addition. The order in which you add vectors does not matter. Commutativity of addition. If we had a vector, an inner product, so we've got the inner product of V with A W plus bz is equal to. Let's try and simplify this down a bit. If I were to say, um, I've lost my train of thought. I've totally lost it. Uh, maybe I've been going at this too long. How long has this been so far? Totally lost my train of thought. It's so annoying actually when it happens. How do I even get to where I'm streaming? Content, live. Here it is. How do I watch this live? Oh God. How do I see how long I've been doing this for? Draw video customer analytics. Not seeing it yet. Back. Um, this is annoying. It's usually much easier than this. I must have clicked a button somewhere. Go live. Ah, I found it. Okay. 1 hour 17. Okay, it's not been that long. Alright, give me a second. Yeah, wow, I just totally lost track. So I think it's because I was talking about the fact that I understood maybe um intuitively, but I hadn't added all the strings to it. So now I'm working with equations that I don't know how to play with. Um, and I still see intuitively what it's saying. It's very obvious, but to actually be able to play with them is really frustrating me. So if I were to just eradicate all this stuff for a second, it's trying to tell me something really important here, but that I should be able to work this out myself, right? Otherwise it's completely useless to me. It's saying that there is this symmetry. Okay, that's fine. I think I understand that because we've already come up with those axioms that are true. But then it says um, that this is also the case where you can move the coefficients out as long as you. It's just telling me a rule. But should I know this rule um, already? If I continue, it's got the next one, which is a. I don't know what star is. What's a star? What does a star mean in the following context? Maybe it means by BI, and I don't know what that is. A W plus B Z V equals B A W plus B Z. Alright, let's try this again. Let me just double check I've got this right. So actually I'll just put a little space in between to make it a bit easier for me to see. AW plus BZ, VAW BZ, A VW BW WV VZ VZ ZV. And also, what does BI mean? Okay, here we go. The asterisk in the context represents the complex conjugate operation. As mentioned before, the complex conjugate of a complex number is its negative. This operation changes the sign of the imaginary part of the number. When you're working with complex coefficients a and b, the operation a star represents taking the complex conjugate of a. So, if a equals x plus yi, then a star equals x minus yi. As for BI, in the context of quantum mechanics, and particularly in the Book of Principles of Quantum Motion, it often refers to bracket notation. The term bracket is a pun by physicist Paul Dirac, combining bracket into bra and ket. Bra denotes a row vector and ket denotes a column vector in the context of complex vector spaces. It's a notation used widely in quantum mechanics, however, without further context, I can't be sure. No, that's fine. Okay, well this does make sense of this. And we were talking about the complex conjugates. Um, so in the equation here, it's saying that um, if was multiply became a complex number, uh, a plus, or let's call this, then uh, then we should do a negative. I don't really understand what it's saying. I'm quite confused. Let's see what this says. If we have a complex number like a plus bi, taking the complex conjugate result, yeah, we got this. In the context of your equation, if you have something like that and you see an asterisk beside it like that, it means that you need to take the complex conjugate of everything inside the parenthesis. If a and b are complex numbers, meaning they have a real part and an imaginary part, then you change the sign of the imaginary part for each of them. For example, if a equals 2 plus 3i and b equals 4 minus 2i, then a, the conjugate of a, is equal to 2 minus 2i, and b, taking the complex conjugate of a complex number, or in this case a more complex expression, has implications for the inner products involved. In quantum mechanics, the complex conjugate of an inner product changes the order of the vectors involved. For example, is equivalent to, let me know if you need further clarification. It's all kind of abstract, and I feel like it's losing me. I think what I'm going to do is I'm going to go ahead, let my brain simmer on it, and then I shall come back to it again and try and understand it better next time round, because it's dropping me in the deep water, I think. Let us continue with inner products. No, let's read this again. Which expresses the anti-linearity of the inner product. So okay, so this I can get the intuition for, and this one is saying that you take the complex conjugate of A multiply that by bra v ket w, or inner product of vw, take the complex conjugate of that. Oh, I see, it's the same as doing that because, ah, yeah, I see. Well, at least I understand this part. So, if I were to take the complex conjugate of this, fucking can't do an asterisk because I'm an idiot. And then, so you would do, um, well, so they're taking them out of the brackets, of course, because you don't need that. So let's say that that is equal to that. And then, ah, but taking it out of the brackets means I have to do it to both. So I've got here we go. I see. But that also means I've got to do it to this. So I've got to go there, 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 and there. So I'm going to do that and that. And that equals, let's see, um, what's the BI again? Bracket, uh, bracket notation. Okay. Let me just ask one question here. You said, why is it I rather than BN? Identity, I see. Okay. In this case, if I were to plus these together, what do we get? We get a complex of a W is equal to negative, I guess. I mean, is this what it's going on about? Uh, this also would have to happen. Is that what it's saying? No, it's not. It's saying that taking the complex conjugate of that. Oh, I see, because you've already scaled it by it. Oh, wow. Okay, that's interesting. I see. It's saying that this is even, just the same as this. Ah, that is interesting. Which expresses the antilinearity of the inner product with respect to the first factor. So, okay, when it comes down to this equation, um, when it comes down to this equation, um, who found this out to be true? Is this something that anyone could have worked out quite easily, or is this a discovery that took many people and many years? I ask because I'm trying to understand if I am expected to know precisely how to have um, gathered this insight myself, or if they are telling me this because it's actually not obvious and needs prompting. Yeah, I'm getting confused at what I'm expected from it. The mathematical results and techniques in quantum mechanics, such as those encapsulated by the are the products of many years of work by several prominent physicists. In the case, the BI refers to a property of inner products in a complex vector space, and it's a fundamental aspect of quantum mechanics that was developed over a long period of time by many contributors, not something that an individual is typically expected to derive independently. The primary developers of the notation and formalism we use in quantum mechanics include Paul Dirac, who introduced the bracket notation, and John von Neumann, who developed the rigorous mathematical foundation of quantum mechanics. When studying quantum mechanics, you're generally not expected to independently derive all these results and methods. Rather, you're expected to understand them, know how to use them, and perhaps know how to derive them from more fundamental principles or definitions, depending on the level of your course of study. Understanding the proof and significance of this identity is part of mastering the concepts of quantum mechanics. But remember that it is built on the shoulders of giants. It's okay if some of these ideas don't seem obvious at first. Quantum mechanics is a complex field that challenges many of our intuitive ideas about the world. It takes time and practice to fully grasp these concepts. Okay, well, as a concept, this feels intuitive, but to prove it, I mean, to go about proving that those things are accurate, then we're using all the stuff that we've learnt before and then assuming that it applies to this. Um, whew, it's quite heavy, isn't it? Um, I mean, how would you prove this? You would, let me see. If we were to take, if we were to take something like, um, well, let's do 1 plus 2i, um, plus 2 plus 2i, and we were to take the complex conjugate of this. So what is 1 plus 2i plus 2 plus 2i? So the first question is how to plot this. I think it's in fact let me let me let me copy this over, and we'll work from there. Yeah, like that. And I think we'll just grab a little snippet of this as well. Makes it a little bit easier for me. Like so. Okay, zoom back in again. Good. Let me move over. So I'm gonna try something here, which is just to simplify it with numbers. And I want to know plotting complex numbers on a graph. I think it's just like negative 1 to 1 and then I to negative I or something like that. Uh, let's see. Yeah, it is. Let's draw that then. I to negative I. Oh, no. I to negative I. That's what I meant to do. I wonder why it's capital I there. And this is negative 2 to plus 2. So if I was to plot this 1 plus 2i, I tell you what, let me just ask as well, if I were to want to, um, I feel like I want to understand this better by trying with a more simple start. If I were to want to plot 1 plus 2i plus 2 plus 2i on a complex plane or complex graph, how do I go about doing this? equals 3 plus 4i. Yeah, okay. This represents a complex number where the real part is 3 and the imaginary part is 4. So it's 1 and then this 1 plus 2i plus 2 plus 2i complex conjugate equals 3 minus 4i. And just to be sure, the complex conjugate of the above would have been 3 minus 4i. Yes, okay, cool. 3 minus 4i. Good, okay. And so if we're going to plot this, we're going to get 1 plus 2i, so it's uh, 1 plus 2i here, and 2 plus 2i, 2 plus 2i here, and the complex conjugate is the opposite of this. 3 uh, 1 plus 2i, negative 1 plus negative 2i. No, 1 negative 2i. It's over here and over here. So this is the conjugate. Um, and so right, and then if we scoot back to this thing, this is saying that um, if I were to do 1 plus 2i complex conjugate plus no, I don't think it is actually. No, no, it's not. It's saying if I were to scale, oh boy, if I were to scale this, yeah, so this is a bit wrong actually. Plus 2i. Let me try this again. If I do a 1 plus 2i plus um, b 2 plus 2i, and then took the complex conjugate of that, that is equal to saying that the um, a complex conjugate times, well, times 1 plus 2i. Well, we could just do this with one side, can't we, really? Like, oh, no, no, I can't. Okay, okay, I see. I'm getting somewhere now. Haha. Be this 2 plus 2i. Yes, 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 yes. This is what I wanted. Um, this is fine, but now if I were to say a equals 2 and b equals 4, if I would have done the scaling, it would be up here. And let's just imagine this is the scaled version, right? So let's just imagine that is it there, because I've multiplied this one by 2 and this one by 4. So let's say it's over here, right? Now taking that, if I were to then plus them together, I get something like this over here, right? Whatever it may be. And then, if I were to do the complex conjugate first, which would be down here, this one here, and then multiply that by the normal one, 1 plus 2i, which is up here. No, 2. Okay, because a would have to be a complex number by itself. But then, oh my god, what? Yeah, so a would have to be a complex number by itself. It's simply saying that if a was a vector, yeah, this would also okay. Let me do this again. I understand this now. This is going really well, actually. Doesn't look like it is, but it is. I think this would have to be. Um, let's try 2 plus 1. Oh, 2 plus I. Well, 2 plus 2i, and then let's do this 2 plus 2i. Fine. And so now, if we took a graph, let's do it like this, and we were plotting 1 plus 2i. Let's say it's kind of like this. 1 plus 2i. It's kind of like there. Plus, so 1 plus 2i times 2 plus 2i. So 2 plus 2i is over here. So if I were to times that, if I were to times the red by the purple, 1 times that. Let me just figure this out for a second. So if I go 1, 2, and then I'm going to times by 2, 2. 2 times 2 is 2, and this is going to be 4. Yeah, so it just ends up being this, I think. Good, okay, we get this. Right, so if that's the case, now it's saying that if you took the conjugate of a and then multiplied by it, it would be exactly the same. So if I took the conjugate of this, it'd be down here, and then I don't even need to, let's see. Yes, a is down here. So I want to take the conjugate of that, but multiply it by that. So if I did negative 2, um, no, 2 negative 2, sorry, 2 negative 2 multiplied by 1, 2, we're going to get 2, negative 2 times 2 is negative 4. Oh, which means that my new output is 2 my new output is 2, -4 over here. This one. Ay, 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 ay. And then if I plus this one as well, it's going to be equal to the conjugate. Oh yeah, of course. Yeah, yeah, because this is the conjugate as well. Yeah, so this, the conjugate of that is that, and so that is exactly equal. Okay, I've got it. No worries. We got it. We got it. We got it. All right. I've actually got some tangible evidence that I've actually got it now. Yes. I totally forgot that I was supposed to. This is in the bracket, so I'm going to do the conjugate of this is equal to the conjugate of the other one plus the other conjugate. And of course that makes sense because if you've got two conjugates, you're going to extend that vector down into the negatives, and so the negative of the other one is still going to be equal to the same one. This makes sense to me. All right, good. Yes, 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 yes. We're getting somewhere, guys. We're freaking getting somewhere. Oh man, that hurt my brain. It's so simple, right? It's so simple, but I think when you're just presented with so many bloody numbers and letters, I feel like a Picasso painting inside my head. Um, okay, right, good. Let's continue then. Okay, so it says, which expresses the antilinearity of the inner product with respect to the first factor in the inner product. In other words, the inner product of a linear superposition with another vector is the corresponding superposition of inner products if the superposition occurs in the second factor, while it is the superposition with all coefficients conjugated if the superposition occurs in the first factor. This asymmetry, unfamiliar in real vector spaces, is here to stay, and you will get used to it as you go along. Now, it's trying to say something that's not familiar to us, but I feel like we drew something very familiar, so maybe I have actually done a mistake here. It expresses the anti-linearity of the inner product with respect to the first factor in the inner product. First factor. I drew the above out and came to the conclusion um, that, of course, if you had the following equation, a um, after a bit more fiddling, a 1 plus 2i plus b 2 plus 2i is equal to a 1 plus 2i plus b 1 2 plus 2i. I came to the conclusion, after a bit more fiddling, I drew the above out and came to the conclusion that, of course, if you had the following equation, they would be equal. Um, you can see this visually by drawing the complex plane, and you can see that the inverse, or the output of the left side is in the negative of the complex number, of the I, and then so is in the positive of the yes, it's in the positive, is in the positive of the I, and then you multiply that by the negative, the conjugate, and it puts it into the negative of the I. On the right hand side of the equation, the same goes. If you I see. A equals 2 plus 2i, b equals 2 plus 2i. On the right hand side of the equation, the same goes. If you um, took the negative, um, if you drew out the conjugate of A um, and B, and then um, added them to the positive version on um, within the brackets, then of course it too goes to the negative of I. They are equal. However, if I move on to the next point it makes, um, this asymmetry, unfamiliar in real vector spaces, is here to stay, and you will get used to it as you go along. I'm not sure I follow. Um, are we saying that if we had, yeah, yeah, I'm not sure I follow actually at all. This refers to a unique property of complex vector spaces which is different from real vector spaces. In real vector spaces, order doesn't matter when you're performing operations like dot product or inner product. This is known as commutativity. But in complex vector spaces, order does matter. The inner product UV is not generally equal to VU, but to its complex conjugate. This lack of commutativity, the fact that swapping the order of the vectors doesn't just give the same result, introduces an asymmetry that doesn't exist in real vector spaces. As you study more and more, you'll come to find that the asymmetry becomes a normal part of your mathematical toolbox, just like complex numbers themselves. Uh, Let me just think about this then. So if we focus back up on, oops, oh no, the app's crashed. There we go. If we focus back up on this equation, we're talking about swapping inner products and not just the operation that we were investigating. I see. So part of me wants to see a normal dot product as well. Um, the dot product of W and V and V and W would be the same because it's the addition or the sum of the products, which is commutative addition. But in the fact of a quantum state, if we were to do W and V and W, is saying that one is equal to the conjugate of it. So, oh, I totally missed this. Oh, this is interesting. I totally missed this here. It's just saying that this is equal to the conjugate of it. Uh, you can do any fancy swapping of addition. No, no. You, aha, aha. Ah, It's just the in. Ah. I feel like if I could be bothered, we could probably draw this out again. Let's see. We would have to do a vector. Okay, let's see. Is it possible to take? Well, let's do this again. In the context of in the context of um, can we does uh, given that it's asking us to take the conjugate, asking us, considering that it's talking about a conjugate, do we infer that the vectors, that the um, scalars or vectors are complex, or can normal numbers have the conjugate too? Not scalars and numbers. The start operation indicates complexity. So this would typically imply that A, W, B, Z, and are complex. In the context of quantum mechanics, the elements of a quantum state vector are complex numbers, so the vectors W, Z, and V are indeed complex. For real numbers, a complex conjugate is simply the number itself because a real number has zero imaginary parts. Um, where does the word conjugate come from? What's its etymology? Comes with Latin conjugatus, which is the past participle of conjugar, meaning to join together. In mathematics, conjugate has a few different meanings depending on the context, but they all have a common theme of pairing or joining in some way. For example, complex conjugates are pairs of complex numbers that have the same real part and opposite imaginary parts. Similarly, in algebra, the conjugate of a binomial is another binomial with the same terms but with the sign of the second term flipped. The term was first used in the mathematical context in the 16th century. It's a metaphorical use of the Latin term indicating the pairing of or yoking together of two quantities. Okay, fine. I see this, and it does assume that it does assume in the notation of Bra and Ket, because it's quantum mechanics, then we should treat it as complex. So what we could do is we could replace every single one of those with a complex like vector or complex set of numbers, like the scalars, right? We could draw them out and prove that equality. Then we could do the same for normal numbers, take their inverse and see that difference. So let's do that. I feel like it's worth the time. Let me just do a blood test. See how we're going. Yeah, I'm going low. Okay. Um, fine. Do I stop or do I continue? I think I'll just take a quick break. I'll go and get my sugars done. So let me just add a little sign here. How do I add a source? Here we go. Text. Aha, I see. Um, be right back. And then I can show that, I think. Alright, cool, good. Let's do that then. I'll be right back. Alright, back. Okay. So let's do this. I think it's well worth it. I'm going to once again take a copy of this, pull that over to, oh, we're going to go down, are we? Okay. Let's see, we're going to go down here. Oh, nice. That's not quite what I wanted. Ah, well, let me just take another snip of it. And I suppose this one will be um, complex, and this one will be uh, real. Right, let's do that. Let's start with the complex. Good. Just zoom out. This is getting a bit slow again. It doesn't. The whiteboard. I can't tell if it's the laptop or the whiteboard itself. Is once you get a bit of information on it, it starts to get a little bit slow, which is a shame. But it's an old laptop. It's Surface Pro, Surface Book 2, so it does have a kind of hefty graphics card in it. What is it? 1060 or something GTX. A little bit of a shame. Okay, right. So, let me close this. For the complex, let's draw this then. No, do we need to draw it? No. Yes, we do. And I wonder, is there a way to add a graph here? Let's see. Graph. No. In fact, let me go to Desmos again. Just grab a copy of this graph basically, like that. Let's get a 30 in there, I guess. Okay, plot that there, and plot that there. Good. Okay, let's get back to this. Ah! Okie dokie. Yeah, right. If we were to draw this out as complex, we would have to do. This might need to be a bit smaller, to be honest. Whoa! What the hell? Right, select that again. Let's try that again. Oh, that's really. That's really shit. Oh my god, that's so funny. Nice, well played. Um, let's try this. So, let's say a is equal to 2 plus. No, let's not be weird. Well, okay, no, let's be weird. Let's do 2 plus 2i, right? Let's make b equals 2 plus 2i. Let's make w a well, you know what? Actually, I wonder, can we just do this with one coordinate? But let's just anyway. So let's make this. Yeah, let's just do them all. 2 plus 2i, 2 plus 2i, 2 plus 2i, 2 plus 2i. And then, well, even such, I could just do that, right? And in fact, let's just take this notation off. There you go. And then z will be the same, 2i, 2 plus 2i, and then v will be 2 plus 2i, 2 plus 2i. Okay, cool. If we were to multiply this, um, oh, this is going to be interesting. I'm looking forward to seeing this. This doesn't make sense. Like, intuitively, you wouldn't think it would be the inverse. That becomes equal. Um, and it's the inner product. So I can't quite remember the calculation here, but how do I do an inner product of two vectors? A 1, 2, 2, b equals 2, 2. Okay. A times b1 plus b2. In your case, both vectors are 2, 2, so 4 plus 4 equals 8. Good, okay. Then the we need to first calculate what the pluses are. So it's going to be a times w, so a times aw is equal to 2, well, is equal to 4 plus no, it's equal to 2 plus 2i, 2 plus 2i. So it's going to be 4, that one, and then put 4 plus 4i plus 2, 4i plus 4 2i is 2i squared. 4 plus 2 times 2i. Let me just do this again. I think I've done this wrong. I'm a bit crappy at these things actually. Well, at least I remember something about it though. So it's going to be 2 times 2 is 4. Good. Then plus 2i. 2 times 2i, so it's 2i squared plus 2i times 2i. Oh no, 2 times 2i. 2i's is 2i squared, and 2i times 2i is 2i squared as well. We can add these together. Is it 2 plus 2 is 4? So it's 2i cubed, is that right? Oh, I can't remember. Let's not skip ahead for a second. Plus, and then you've got 2i, well, it's 2i squared plus 2i squared, isn't it? Um, am, oops, am I right in saying that if a equals 2 plus 2i, if a, b, w, z, if b equals that, and w, z, v equals 2 plus 2i, 2 plus 2i, then in the equation aw, 2, 2 plus, whoops, 2 plus 2i, 2 plus 2i, our first step would be 4 plus 2i power 2 plus, and then that times 3. You're close, but there, a small mistake. When you multiply complex numbers, you apply the distributive property similar to how you would with real numbers. Let's see how this works. When calculate AW, you would do 2 plus 2i, 2 plus 2i. Applying the distributive property gives you 4 plus 4i. Okay. And then that's 4i squared. So let's try this again then. I knew I'd done something wrong. 2 plus 2 is 2 times 2 is 4, and then we've got 2i's is 4i. I see. Okay. And then plus 2i times 2i. 2i's is 4i plus 2i times 2i is 2i squared. Remember that I squared equals -1 in the context of complex numbers, so this simplifies further to 4i squared. Wait, so let me check this out. AW equals would actually be 2 times 2 plus 2 times 2i plus 2i times 2 plus 2i times 2i, which would equal 4 plus 2i is 4i plus 4i plus 2I to the power of 2, which would equal I to the power of 2 equals negative 1. 4I, so which would equal negative, so I to the power of 2 is negative 1. Negative 1 times so at 4 plus 8I. 4I plus 4I is 8I plus um, minus 1 times minus 1 is 1. Sorry, no, how does it work? I always forget this. 1 times negative 1. Oh, it didn't work out. Let's try it again. Negative 1 times negative 1 equals 1, yeah. Because negative 1, because I to the power of 2 equals negative 1, 2 times negative 1 equals 1. Therefore, the equation would be 4 plus 8I plus 1 equals 5 plus 8I. There's a small mistake in your calculation. You correctly noticed that I is to the power of 2 equals 1, but then in the calculation you stated that 2I is to the power of 2 equals 1, which is incorrect. Here's the correct calculation. Why is it... What? What's 2 to I? 22 plus... okay. 4 times minus 1 because I to the power of 2 equals negative 1 and 4 times negative 1 equals negative 4. No, that can't be right. Equation solver. Eight I. Um, equals 8I. So where did I go wrong then? I'm such an idiot. Oh, I love it. I thought 2I times 2I. It's because I is its own term. So you do 2 times 2 is 4. Is 2I times 2I very different from 2A times 2A, which would be 2. Oh yeah, I am an idiot. Okay, cool. I got you. Right, okay, let's do that again. Ha! Ooh, this is fun. Okay, so it'd be 4I squared, and then therefore it'd be 4 plus 8I plus 4 times negative 1. I didn't need that. I'm trying to undo. It's not actually doing anything, unfortunately. It's crashed. 1 second. It'll work now? No, it can't undo. Let me just close this and reopen it. Sorry. sometimes the yeah, whiteboard doesn't let you undo, which is quite funny. Should have turned this off as well. Try again. All right, cool. Let's get into this. Yes, okay, back. Right, let's try it again. 4 times -1, so -1 times -1 times -1 times -1. 4 -1s. Um, I squared equals -1. 2 times -1 equals 1. So it's +1 again, yeah. 4 plus 8i plus 1 equals 5 plus 8i. And then it says, oh, 4 plus 8. But this one says 8i. Which intrigues me. Why is it only 8i? 4 plus 8i, -4. Oh, I see. So 4 times -1 because I squared equals -1 and 4 times -1 equals -4. I see. Ah, this is nice. Okay, I got it. Let's do this again. Ah, one day I'll learn. So 4 plus 8i plus 4i squared is, so it's I squared equals -1. And then 4 times -1 equals -4. So plus, actually it'll be minus -4 equals 8i. Yeah, alright, cool. We got it. Good. Um, Fine, so we now know that AW is 8i, and this would mean that all the rest are 8i, right? That's why I did that. So then, if we were to plot that, let's go 5, 6, 7, 8, 8i. It's gonna be there. 8i. It's gonna be there. Like that. Can you see that? Yeah. Good. Okay. Cool. So it's saying that if we invert that, then it comes out differently. So I'm very interested now. Let's see. See if I can budge this up a bit. You might not be able to see that anymore, but it's irrelevant. You've seen it already. So let's just put that there. So if I did um, let's see, it's going to be 8i, which is that, plus 8i, which is that, and then the inner product of um, right, I see. Yeah, we actually need to do this properly because no, that's right, that's right. So it's 8i plus 8i. Oh no, this is interesting. No, no. Um, it's just one, isn't it? It's going to be 16i. However, I'm a little bit concerned here because now, yeah, but no, I see. It's actually w is equal to Um, aha. Okay. Yeah, this is wrong assumption here because that's just for one of them. So that's going to be 8i 8i, right? Because I'm doing a times w, a times second component, and then I've got to do um, then I have to do uh, yeah. It's okay. Okay, so w equals that, and then I do aw is going to equal no, because we've already done that. I see. Yeah. Okay. That's it, isn't it? Yeah. It's 8i. So then if we plus that to z, which would be the same, then we're going to get uh, yeah 16i is our new one, right? aw plus bz equals 16i. And then we're going to multiply that. No, we're going to do a let's call this p. We're going to do p. Oh god, I can't write. The inner product of p and um, v, which which is equal to 16i 16i uh, um, um, da, 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 2i 2i no 2 plus 2i like this. Okay. Whew, okay. So let's just double check because I feel like I'm mistaken this somewhere. Yeah, we're at the point where the coordinates, the components are 8i. Can I still hear myself here? Let me just double check this. Yes, I can. Whew. I was worried that I like somehow my headset's gone off, but it hasn't. So we did 8i, 8i's 8i. So then you plus them together. Then we've got our new vector, which is aw plus bz, which we're going to call p, and then we're going to take the inner product of p and v. And v is only 2 plus 2i still. We haven't done anything with it, right? Now this is where it's going to be interesting. So yeah, I'm not feeling this diagram at the moment. Let me just try and get rid of this. Something's going wrong with this bloody tool. Come on, Microsoft. Give me a break, dude. We're not ready to draw that yet, essentially. So, given all this, let's take the inner product, which is going to be 16i times 2 plus 2i plus 16i plus 2 plus 2i. 16i plus 2 plus 2i. Oh my god. Uh, and this is, oh, this is multiplied, sorry. Yeah. Um, it's going to be 2. Uh, let's see. It's actually this, isn't it? Let's try that. There you go. Something like that. And that's going to be equal to 2 16s. What is that? 16 times 2 is 32. 32i. That's that one. And then it's going to be 16i times 2i is going to be, wait, 2 times 16i is 32i, and then 16 times 2 is 32i, which is equal to 64i. Alright, okay. So it's going to be, therefore, 64i plus 64i equals 128i. Okay, so let's just double check that again. And if I were to, understood. Now, if I were to um, put that back into an equation, um, where is it again? Uh, with the following um, variables, the equation being AW plus BZV, we would W equals 8i, 8i, Z equals 8i, 8i, therefore 8i plus 8i equals 16i, therefore 16i, let's see what we got here, is it 16i? Oh, did I do this wrong? No, therefore 16i b, let's make 16i equal to p. P equals 16i 16i 2 plus 2i 2 plus 2i p v equals 16i 2 plus 2i plus 16i 2 plus 2i, which equals 32i plus 32i, which equals 64i. Therefore, oh, I think that was just for the, yeah, I think that was just for, that was for the whole thing, wasn't it? So I've got here um, the inner product part here, which would equal 16i times 2 plus 32i plus is 64i, and then it's plus 16 is 32 plus 32, 64 plus 64. Therefore, um, it equals 32 plus 32i Let's do that. Wait, how do I denote this? Um, so I'm a bit confused here. So, but I'm on the right track. I'm on the right track definitely. So I've done this times this is 32. Then I've done, that's not very clear, is it? Done this time this is 32. Then I've done this time this, which is 32, plus, um, and then that was two. That was one of them. So it's just 64i. That's it. Because I had AW, which is AW plus BZ equals 16i, 16i. That's correct because those are 8s. And then that's the left side. So it's now 8i, 8i. It's now 16i, 16i. The dot product of two, and to do that you do this um, and this. So we've done that and we plus them together, which is 32 equals 64i. Um, is this correct? Please just say yes. Oh my god. When performing an inner product operation, we must multiply each corresponding pair of components in the vectors and add the results. In the complex numbers, the conjugate of the second vector's element is usually taken. However, in this case, you have real numbers, so there's no need for a complex conjugate. Also, just to clarify, in your example, vectors w, z appear to have two components each, both of which are the complex number, while a and b are also the complex number. Now, if we calculate the inner product, where PV, where P is 69, is 2 plus 2, 2 plus 2, 16 times 2, so 16 times, yeah, remember that I squared equals negative 1. Yeah, but 16 times 2, oh, it's because I squared. Motherfucker. Okay. Okay, let's try this again. Let's try this again. I see. So it's actually, um, it's 16, it's 32i, so 2 times 16i plus 32 times negative 1. So it's actually negative 32. So it's 32i minus 32. 16 times 2 negative, yep, plus 32i minus 32 equals 64i. Oh, wait. Negative 34. Oh yeah, of course. Um, it's 64i minus 64. Yes, that makes sense. Okay, got it. Yeah, yeah, got it. Cheers. Um, so the next part is then right. We've done it. So now we know so now we need to compare it, right? So this is first one. Okie dokie, easy peasy. That was actually easy. I'm just an idiot. So now let's do the second one. The conjugate of this. The conjugate equals. Ah, no. We want to know if we swap them round, what happens? Aha. So if I were to do um, if I were to do uh, B plus A. No, I see. Um, Wait, how is that going to make it different? So it's the same thing here. AW plus BZ is going to equal AW plus BZ is going to equal 16I. AW is 8I. Yeah, 16I. So then we're going to go, therefore, um, t it's going to be 2 plus 2I, 2 plus 2I. It's going to be exactly the same. So I've done something wrong here. Um, before how is that going to be different? It's not going to be different. So I need. So why do I need to take the complex conjugate to make it equal? Because if I've got 16I or P v P, then well, we just got 2 plus 2I, 2 plus 2I, 16I, 16I, and that's going to equal this 2 times 16 is 32I, 2 times 16 plus 32I plus 2 times 16 is 32I. Oh, whoops, hang on. Have I done this right? Yeah, okay. Sorry, I'm really apologize for this. So, let me just undo this a bit. So first one is 232I. Okay. So 1, then I got this one is 32I. Then I've got no. What am I doing? This is not how you do this. It's just that, and then that. 32I plus 32I. Holy shit! Oh my god, look at that! I must be going insane. Wait, is this? Have we just have we just figured this out? So wait. I must have done a mistake. So it really that's really surprising. So just by turning it round, No, no, no. I must have done something wrong here. Two, two times. Yeah, I've definitely done something wrong here. Definitely. Surely. Two plus two I. Yeah, I have done something wrong. Of course, I've done something wrong. Yeah. Oh, that was shocking then. So it's essentially going to be two plus two I, two plus two I times 16I. Thank you. Okay. Plus that. So it's going to be um, 2 plus 2I um, times 16. So it's actually 2 plus 2I times 16I, which is going to equal 2I, so it's 32I 2 plus 32I. Now did I do this right here then? So this is 16I times 2 plus 2I, which is the same, right? So 16I times 2 plus 2I is equal to 60 times 2 is 32I, and then plus um, it's I squared, so it's negative 1, so it's 32 times negative 1 minus 32. Yeah, so it's the same. Okay. So I've done something wrong here because but yeah, so this is weird because if I if I has taking the above PV or VP makes them precisely equal. So why do I need the conjugate to make them equal? Have I misinterpreted something? For example, by making the coefficient scalar a vector, a two-dimensional complex vector, did I ruin this like that? I think the scalar had to not be. The need to take the complex conjugate in the inner product is particularly important when dealing with complex vector spaces. And these spaces are vectors and the coefficients multiplying them can be complex numbers. When you take the complex conjugate of the second vector's components in the inner product, it ensures that the inner product of a vector with itself is a non-negative real number. This is essential to make the inner product match our geometric intuition that the dot product of a vector with itself. In your case, you were dealing with complex numbers, but you weren't actually performing an operation that required considering the complex conjugate. Instead, you were doing a simple multiplication of complex numbers and adding the results. So for the question PV versus in a general complex vector space, these would not be exactly equal, but would be complex conjugates of each other. If the coefficients are real, then they will be equal because the complex conjugate of a real number is the number itself. In your specific example, you have indeed made the calculation more complicated by introducing complex coefficients and a multidimensional complex vector. If you simply started with real coefficients and real vectors, the inner product would be much simpler and PV would indeed be. Remember, the need for the complex conjugate is there to make the mathematics consistent with our geometric understanding of the inner product in a complex vector space. It is not so much about making things equal as about ensuring the properties of the inner product hold true. Um, so I've kind of lost it a bit again. Oh, I'm going back high again now as well. Bear with me, just going to do injection because I'm diabetic, going to go a little bit high. Okay. Um, well, I'm confused. I don't really know what I've done wrong there yet. And I could do it all again. Um, I mean, let's just do that. If I were to just do it over here, get rid of this again, don't really need it yet. And this would be complex, and I shall move my page over. Oh, it's broken again. Gonna work? There we go. Okay, so let's do this again. If wait, take this stuff. Uh, that can go there. Yep. Okay. But this time we're just gonna do that, right? So now if we do it, we've got 2 times 2 plus 2i and plus no sorry 2 times 2 plus 2i, which is equal to um, let's just do that because it's a bit confusing. It's going to be equal to 4 plus 2 times 2 is 4i. 4 plus 4i. Okay. Uh, so therefore w, z, and v are all equal to 4 plus 4i, or a that. Yep. And so then I can say, well, a 4 plus 4i plus that's that one, and then we'll do the bz plus 4 plus 4i is equal to we're going to call this wrong way around. Whoops. I think I always do that. There we go. It's going to be equal to p. So p is equal to 8 plus 8i, right? 4 plus 4 is 8. 4i plus 4i is 8. 8 plus 8i, okay. And that's p, so then... Ah, well, is it now? It's not, it's actually 8. 8 plus 8i, yeah. Okay, so then what's p w? V, sorry. Well, if v was... If any of those was... so, okay, v is... Let's just do that first. V is equal to 2 plus 2i. No, it's not. It's going to equal to... yeah, v is equal to 2 plus 2i. 2 plus 2i. Let's move that across. Now, are we happy with this? I'm doing 2 times each of the components, so that makes them 4 plus 4i, and then I am plus 4i. Whoops, undo. Then I'm doing uh, and then I'm adding them together. So I've got 4 plus 4i plus 4 plus 4i, and that is going to be w, and that is z. And so that's now. I've basically skipped some of the coordinates there, but that's basically it. They end up as that. Yeah. Uh, Let me be sure here. So I've got that. This is AW equals that, and then because they're all equal to that, therefore AW. So because they're all equal to that, 4 plus 4i plus 4i equals 8. 4i 4i. Here we go. This is where I went wrong. 4 plus 4i. There you go. Okay. Uh, let's do this now. Therefore, P is 4 plus 4i, 4 plus 4i plus 4 plus 4i, 4 plus 4i, and so then we're plussing together, so it's just going to be 8 plus 8i, 8 plus 8i. There's that, and then v is equal to 2 plus 2i, 2 plus 2i, and so um, PV is equal to um, 8 plus 8i, 8 plus 8i, didn't mean to do that, 2 plus 2i, 2 plus 2i, and so now I want to do this, no, oh, did press that, this, and then I want to do this. And you plus them to each other, so that means that PV is equal to 8 plus 8i multiplied by 2 plus 2i. Yeah, I think I kind of went wrong last time, but so it's 8 times 2. Let's do this here. Oops. 8 times 2 is 16, and then so it's that, and then 8 plus. No, no, no. It's 8i times 2 is 16i in fact it's 8 plus 16i plus this. 8 times 2 is 16. It's going to be negative 16. So then it's going to be 8 mass 8 plus 16i minus 16, which means um, plus 8 wait. Oh my god, why is this so hard for me? You can see I just don't do this enough. Let's try this again. 8i times 2 is 16i. But I need to make sure that I've got the 8 here. So 8 plus 16i plus I squared is -1, so 8 times 2 is -16, so it's 16i minus 16. Therefore, 16i is -16i is equal to 8 minus 16. -16i is equal to uh, -8. Okay, so let's take that. And now if we were to swap this round so that v is the inner product of p, it doesn't make any difference. I don't understand this at all. Um, I went ahead and changed the scalar coefficient to a single number. I now have a equals 2, b equals 2, w equals 2 plus 2i, 2 plus 2i, w, z, w, z, and v. Which means aw is equal to 2, 2 plus 2i, 2, 2, 2i, which equals 4 plus 4i, 4 plus 4i. And because aw is exactly the same as z bz, oh my god, I pressed the wrong thing, bz, oh wow, what have I done? Oh, I went to Greek, haha. This one as bz, then we end up with p equals plus equals 8 plus 8i, 8 plus 8i. Okay. Therefore, then I worked out the inner product. PV equals this, oops, that, and 2 plus 2i, like that, which equals 8 plus 16i minus 16. Is this right so far? Or negative 16i is equal to negative 8? Whoops. You quickly compute a, w, and bz, okay? Now you're adding these vectors together to form p, but you've duplicated each vector. Since each vector is just a single complex number, the sum p equals aw should also just be a single complex number. So the correct sum is Well, I mean it's coordinates though, right? Isn't it? Then to but W is a coordinate. Is a two-dimensional complex coordinate. The commas were simply to represent the coordinates in that vector. Um, Complex vector. The commas were simply to represent the components in that vector. Correct that. So now bz equals 4i, and there's some p equals aw plus b is 8. Yeah, cool. Then the inner product is given by 32 plus 8 plus 8i is 8. Oh yeah. Wait. Oh yeah, of course. Oh yeah. Wow. Wow. Okay. It's. I need to multiply the equations, don't I? Of course. I'm glad I asked this then. Of course. Of course. Yes. Um. Yeah. Okay. 8 times 2 is 16 plus. Let's do this then. So 8 times 2 is 16. 8 times 2i is 16i. 8i times 2 is 16i plus, actually minus 16. Um, and so, that's going to be equal to 16i plus 16i is 32i. 16 minus 16, it's just 32i. Oh god. Let's see, 16 plus 32i minus 16. Where did I go wrong here? 8 times 2, 16, plus 8 times 2i is 16i, plus 8i times 2 is 16i, minus 8i times 2i. I squared is minus 1. 8 times 2 is 16, negative 16. Um, oh, where did I go wrong here? 8 plus 8i, 2 plus 2i is equal to 16 plus 16i plus 16i plus, oh, minus 16. Minus 16 because I to the power of 2 is negative 1. Therefore, 32i let's see. It's going really well so far, isn't it? Let's see. 16 plus 32i minus 16 equals 32i. The correct computation would be 16 plus 16i plus 16i plus 16 minus 1. Huh? 16 times minus 1, not 16 minus 1. 16 plus 32i minus 16 equals 32i. That's what I just said. Wait, well, I just said that, so I think it's getting confused now. Yes, this is 16 minus 16 equals 0. 0 plus 16 um, I plus 16i equals 32i, right? That's what it's got. Um, how did I? So it says if we're dealing with two-dimensional complex vectors, then the inner product in this case is this is 32i, 32i. Uh, oi, oi, oi. Oh yeah, because we're adding them. No, 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 no. This is each side, and then we're adding them together. 32 plus. Oh boy, oh boy. Um, what am I doing wrong here, eh? So this is a coordinate. Okay, so that means that both the coordinates are going to be the same, and it's because it's you multiply them and then you plus the values together. So you got. Let me try this again, and let's just do this so I don't get confused, because clearly I keep getting confused. Yeah, I gotta multiply them together and then plus the results. So this is 32i because 8 times 2 is 16 plus 16i plus 16i plus no minus 16, which is equals to 32i, and then that was just me multiplying them together. So now I've got 32i plus 32i equals 64i. That has to be right. Um, 32i plus 32i plus 32i plus 32i. How do I compute dot product, inner product of 8 plus 8i, 8 plus 8i of v equal of p equal and p equals v equals 2 plus 2i, 2 plus 2i, or in other words, p v. Would it be 8 plus 8i times 2 plus 2i plus the same equals 32i plus 32i equals 64i. There is a mistake in a calculation. In the context of complex vectors, the inner product also involves taking the complex conjugate of the second vector. This is due to the property of the inner product that demands that v is always real and not negative. This is due to the property of the inner product that demands that v is always real and non-negative. which wouldn't be the case if we didn't take the complex conjugate. When you compute the inner product of P and V, it should be. I know, but I'm trying to. So this is why it's got a different thing. I see. But how do we get to understanding that we need the complex conjugate without first trying it as a normal geometric, normal real, um, as a normal dot product, inner product? If I start by saying that we should do it normally, PV equals 64I, then we do the opposite, and then we do, in comparison, the conjugate, the correct calculation, using conjugate of um, um, but uh, I'm confused because it says that it's only when you change the order of the inner product do you need to use the conjugate. For example, PV is equal to VP conjugate. Not that PV has to use any conjugates in its own right. Let's see what this says. You're correct, and I apologize for the confusion. In the bracket notation often used in quantum mechanics, when you see an expression like PV, it implies that you're taking the inner product of the complex conjugate of P. On the other hand, when you see VP, it's the inner product. Taking the inner product of the complex conjugate. It's the inner product of the complex conjugate of V and P. The conjugation is implicit in the notation, hence the statement PV equals P in the book. So you're correct that when you flip the order, you take the complex conjugate result, but that's because of how the bracket notation implicitly involves complex conjugation. In simpler terms, if you are given two complex vectors P and V, PV would imply that you're taking the inner product of the conjugate of P and V, and VP would mean that you're taking the inner product. Oh, so it's not actually just saying that. So, okay, so for your original question, when calculating PV, the calculation should be indeed B, and when calculating V, you should get 64. When calculating VP, you should get 2 plus 2 times. Yeah, then you can see that PIV equals the conjugate because 64 is the complex conjugate of 64I. What? I don't get this. Anyone watching, please help. Oh my god. What is going on here? Then you can see that. And when calculating the other way round, but that's enforced, that's pushing in the complex conjugate already. Then you can see that equals because 64 is the complex conjugate of 64I. Let's just show that. So 64 equals 64I because 60 because y 1 plus 64I is the complex conjugate. 64 is the complex conjugate of 64I. 64 minus 1 minus 64i 1 minus 64i, so we're down here somewhere. And then 64 is going to be like over here somewhere. So how are they the same? Oh, I think this is like, how on earth is 64, how on earth is the complex conjugate of 64i 64? Changing the sign of its imaginary part. So the complex conjugate of 64i is actually minus 64i, not 64. In the context of inner, that's better. Um, in the context of inner products in a complex vector space, if we didn't, so I think, okay, I think GPT is confusing me. It's not quite understanding, is it? I apologize for the confusion. That was a mistake on my part. The complex conjugate is, yeah. In the context of inner products in a complex vector space, if we denote the inner product of vectors x and y as xy, it has the property that xy is the complex conjugate of, yes, this means that if, so in your case, if you got PV equals 65, then you should expect VP to be, assuming all calculations are correct, once again, I apologize, but, but, but why does PV equal VP? Um, like, who thought that something should be, like, it doesn't matter which order you do these, the result of inner products without, like, who thought, like, what, what I'm trying to say is, like, why, like, when someone did this, and they, I guess they plotted out, they thought, okay, we can just do this, like, who, like, what's the problem with not taking the conjugate? If you treat all the above complex parts of the equation and just do the math, then the equations do indeed equal each other without a conjugate. So who determined that even though the maths is correct, we need to conjugate it to make them equal? The property V is a general feature of inner products in complex vector spaces. You might ask why the inner product for complex vectors has this property, and the answer comes from the definition of the inner product in a complex vector space. This definition is designed to work well with the mathematical properties of complex numbers, and to preserve certain important geometric concepts when we move from real to complex vector spaces. In a real vector space, the inner product of two vectors is symmetric. However, complex numbers don't behave the same way as real numbers, and this symmetry property doesn't carry over to complex vector spaces in a straightforward way. Instead, we get a related property, AB is the complex. The complex conjugate essentially reverses the effect of the imaginary unit I, which is a fundamentally different kind of quantity than a real number. In order to make the inner product work smoothly with the mathematics of complex numbers, it is necessary to incorporate the complex conjugate into the definition. So it's not that there's a problem with not taking the conjugate, rather taking the conjugate is part of how the inner product is defined for complex vector spaces. This definition is based on the mathematical properties of complex. Um, so so even though in terms of values, these are actually equal, someone realized that regardless of the maths making the two equal correctly, when putting them into other requirements, they didn't work out unless you um, took the conjugate instead. If that's so, I can understand it's simply a matter of being a mathematical tool that makes other things work. But how is like how is this then appropriate maths? It's changing the rules in which mathematics usually works. What problem was this actually trying to solve in the first place? Why didn't someone just say, yep, it's fine that the complex vectors, the inner product of complex vectors is totally fine without the conjugate. No worries whatsoever. Okay, that's my. I think we'll leave it after this because the inner product was generalized to complex spaces in this way because it maintains desirable properties and behaves in a consistent manner. It may seem strange if you're coming from the perspective of real numbers, but remember that complex numbers are fundamentally different. They have two components, real and imaginary, and multiplying them involves a rotation in the complex plane. If we didn't include the complex conjugate in the definition of the inner product in complex spaces, we would lose a lot of the properties that make the inner product useful and consistent. Conjugate symmetry. This property ensures that the inner product behaves consistently with the idea of symmetry in a complex space. Um, I think when I visualize it, maybe with point one, are you referring to some visual expectation? I just don't understand. I just don't understand why. Um, with this definition, the inner product of a vector with itself is a non-negative real number, which generalizes the idea of the length of a vector in a real space. Positive definiteness. If you didn't include the conjugate, the inner product of a vector with itself could be any complex number, not necessarily real or non-negative, but in both real and complex vector spaces, it is crucial that the length of a vector, given by the square root of the inner product of the vector with itself, is a non-negative real number. Linearity, the property a plus bc equals ac plus bc and would no longer hold in a straightforward way. This property is fundamental to the behavior of vectors. In other words, incorporating the complex conjugate into the definition of the inner product in complex spaces isn't about changing the rules or making things arbitrarily more complicated. It's about extending the concept of the inner product to a new context in a way that preserves the most important and useful properties of the original concept. Nope, don't understand it. I don't understand it. um, is there a way of visualizing this? Got anything I can search for to understand this better on YouTube, for example? So I mean, I understand you can represent them, right? We've already drawn these, but there is no problem with drawing. It's not that I don't understand it. It's just it doesn't work, right? I mean, there's no. I'm not being given the answer in which says like you need to do this unless I'm just completely. I'm so sorry. I don't. Can we step back a bit? Imagine I'm Dirac or whoever came before, and I'm here playing with this new tool called an imaginary number, whereby I to the power of 2 equals -1. Cool. I've got a new toy. Now let's play with it. If I if I had the following variables, and I thought to myself, being Dirac and all that, let's try see what happens when we do the following equation. Um, AW plus BZV. Now, at this moment in time, poor old me has no idea about conjugates. So I go ahead and I do the normal inner product math of these scalars and their vectors. I end up with an inner product equal to um, 64i. Then I think, cool, okay, I'd best prove to others that um, reversing this bad boy around makes no difference. So I end up doing that. I reverse it around. The um, and hey presto, when I in presto, not forgetting that me, this make-believe Dirac or whoever, is playing with this new tool for the first time and has no idea about conjugation. I'm sitting here thinking, alright, cool. This is symmetrical, because V equals, and I walk off into the distance as a hero, because now using my new imaginary number tool, everything is fine and dandy and everyone is happy. Now, in 2023, me, James, in 2023, a new noob at maths, James, is being told that actually, nope, um, is wrong and that you have to do this instead. Therefore, James asks, what the fuck? Why? Druck was totes cool with this before he knew about conjugates. Therefore, here I am today asking what made um, what made the change to state no, we need a new tool whereby if someone says I'm gonna take the inner product of two complex vectors, I have got to take the conjugate to make these dudes equal. Right, let's see what happens. Oh, there's a lot of typing. It's fun though. Because you catch my drift, right? That's a clarifying question. The development of the inner product in complex vector spaces is really a tale of two mathematical tools, complex numbers and vector spaces. Firstly, let's consider the simple case of dot product in real vector spaces. The dot product of two vectors is commutative, meaning that AB equals BA. This property is quite intuitive and easy to understand. Then comes the development of complex numbers. Suddenly, we have numbers that have an imaginary part. These complex numbers also have interesting properties. For one, when you multiply a complex number by its conjugate, you get a real non-negative number. When you multiply a complex number by its conjugate, you get a real non-negative number. Well, let's try that. So if I go over here, so I've got 3 plus, well, let's do 2 plus 2i. Um, that's going to be a, and then oops, and then we're going to say 2a. Now it says when you multiply a complex number by its conjugate, so this is the conjugate, you get a real non-negative number. So 2 times 2a is going to be, sorry, that. You're going to get 4 plus 2 times 2i, 4i. And then if you put that on a graph, we get 4, 1, 2, 3, 4, 4, 4i, somewhere up here, right? You get a real non-negative number. So let's imagine b is equal to 2 minus 2i. Its conjugate is the plus, right? So then if I go 2 times 2 minus 2i, I'll get 4, 2 minus 2 minus 4i. So if I do 4 minus 4i, it's going to be down here. Right, maybe I've got this wrong then. So imaginary plane. It is, yeah. Plus and minus. When mathematicians first started playing around with vector spaces over complex numbers, they tried to find a way to merge these two ideas together. They wanted a notion of a dot product that could take complex vectors and give a single complex number. But they also wanted this operation to somehow incorporate the nice properties of complex conjugates. This led to the definition of the inner product for complex vector spaces. The inner product of two complex vectors is defined in such a way that AB is the conjugate of BA. This way, if you take a vector and find the inner product with itself, take a vector and find the inner product with itself, you get a real non-negative number, similar to finding the magnitude of a vector in real space. So in essence, the need for taking the complex conjugate and the inner product came from the desire to maintain some of the nice properties of the real valued dot product, while also incorporating the new tool of complex numbers. It's like trying to find the best of both worlds, or in this case, the best of both mathematical tools. This inner product then became a fundamental tool in the development of quantum mechanics, which relies heavily on the mathematics of complex vector spaces. Let's give you some insight into why the inner product was. It doesn't. It just doesn't. Um, Given what you've said here, if I had a equals 2 plus 2i, uh, and b and z equals 2, then za equals 4 plus 4i. So how is it that when you multiply a complex number by its conjugate, you get a real non-negative number? Is it because the 4 is positive? And similarly, if I had b equals 2 minus 2i, zb equals 4 minus 4i, and because the 4 on the left is positive, this is what you're talking about. The complex conjugate of a complex number a plus bi is a minus bi. I know that. When we multiply a complex number by its conjugate, the imaginary parts cancel each other out, and we are left with a real non. Let's take your first example where a equals 2 plus. The complex conjugate of a would be 2 minus 2i. I know. So you said these complex numbers also have. For one, when you multiply a complex number by its conjugate. Aha, I see. I see. Understood. Yeah. Um, okay, fine. So then comes the development of complex numbers. Suddenly, we have numbers that have an imaginary part. These complex numbers also have interesting properties. For one, when you multiply a complex number by its conjugate, you get a real non-negative number. I've got you. Yes, I see. Yes. Okay. Um, when mathematicians first started playing around with vector spaces over complex numbers, they tried to find a way to merge these two ideas. They wanted a notion of dot product that could take complex vectors and give a single complex number. But they also wanted this operation to somehow incorporate the nice properties of complex conjugates. I'm just reading this to myself because I need to concentrate for a bit. let's take your first example where, um, yeah, which is a real number. In the second example, b, the complex conjugate of b would be 2 plus 2i. Again, if we multiply b by its conjugate, we get 8, which is also real. The statement when you multiply, sorry, yes, I see that I missed your point about multiplying by a conjugate. Um, I still don't understand why does not equal p v. If you listen to the outputs, the equations that come out, they are indeed equal. So why so what so why do we need to conjugate one side? The idea that VP is not generally equal to PV in the complex can indeed be counterintuitive if you're used to dealing with real numbers. In the context of real numbers, the inner product is symmetric, meaning that AB is always equal to BA. Once we enter the realm of complex number, the symmetry no longer. But a complex number is just a tool that says I equals I to the power of 2 equals -1. That's, is that not all that it is? I to a complex number doesn't roll around. However, once the definition is established, complex numbers have. Okay, let me read this. Complex inner products introduce a conjugation operation that breaks this symmetry. This conjugation operation has crucial implications for the mathematical properties of the inner product and, by extension, the entire field of quantum mechanics, blah blah blah. In more technical terms, the complex inner product is sesquilinear, not bilinear, meaning it is linear in one argument but conjugate linear in the other. The conjugate linearity in one argument is what breaks the symmetry between. A key aspect that the conjugate brings to the table is that it makes the inner product of a complex vector with itself a non-negative real number. This is crucial when we interpret the inner product as a measure of length or magnitude in quantum mechanics, where complex vectors represent quantum states. The inner product of a state vector with itself represents the probability of finding a system in a particular state. Probabilities are real numbers between 0 and 1, not complex numbers. That's why the inner product in complex spaces involves a conjugation operation, which makes VP and PV complex conjugates of each other. The mathematical framework of quantum mechanics just wouldn't work as we know it if we didn't introduce this conjugation operation in the definition of the inner product. Again, I would highly recommend referring to a comprehensive source like a textbook or an. Oh, mate, I'm trying. As they're quite subtle and involve quite a bit of mathematical sophistication. Yes, the fundamental idea of a complex number does revolve around the idea that I squared equals -1. However, once this definition is established, complex numbers have a wide range of properties and behaviors that are fundamentally different from those of real numbers. For example, real numbers are ordered. You can always say whether one real number is greater than, equal to, or less than another. This is not true for complex numbers, where no such order is defined. Another fundamental difference between complex and real numbers lies in their geometric interpretation. Real numbers can be represented as points on a line, while complex numbers can be represented as points in a plane, with one axis representing the real part and the other axis representing the imaginary part. There are many other properties make complex numbers a very powerful mathematician tool that goes beyond the simple equation I squared equals -1. They are used extensively in many areas of physics, engineering, computer science, and other fields. Complex numbers are particularly essential in quantum mechanics, where they provide a mathematical framework for describing. Nah, this isn't helping. Okay, what I'm gonna do is I'll take a break because it's not sinking in yet. there's something crucial I'm missing as to why it's not the case. I mean, we did it here. We did sorry, we did it here. We said that, all right, let's take these PV, and we got 64i minus 64. And when we went to VP, we also got the same. Then we thought, okay, well, let's be a bit more simple. We'll just take the scalar product instead. Well, we did that. PV, and then of course taking the inverse of that would still equal the same. Um, Mate, honestly, so confused here. I'm confused because it just doesn't make sense. um, let's do this again. Let's just try it again because I want to make sure I'm actually filling out the whole kit and caboodle here. Um, so A equals 2, B equals 2, WZ equals WZ and V equals that, which means AW equals 2, 2 equals 4i, and because AW is exactly the same as BZ, then we end up with 4i plus 4i equals 8i, 8i. Then I worked out the inner product. PV equals, let me just check my blood sugars for a second. Oh, I'm going low. 1 second. I'll be right back. Alright, back. Okay, so then I worked out the inner product, which is going to be this, which equals um, which equals uh, it's going to be 8 times 2 is which equals 8 times 2 is 16 plus 16, no, which equals 2 plus 2i times 8 plus 8i plus the same, which equals 16 plus 16i plus 16i minus 16, which equals 32i. Now, let's consider the opposite. So consider VP equals which equals 2i 8 plus 8i plus that again, which equals 2 8s is 16. Mate, honestly, so I'm confused here because it doesn't make sense. For a minute, can we imagine that conjugation doesn't exist? And that I am playing with imaginary numbers which have a property of I squared equals -1. So 16 plus 16i plus 16i plus -16 equals 32i. That's it. Therefore, without considering conjugation and just considering the property of I squared equals -1, do you agree that in this very specific case, PV equals VI, even when considering imaginary numbers, complex numbers? No problem so far, right? You're correct. In the specific example you've given, the computations for PV and VP do indeed yield the same result, 32i. However, it's important to note that this is not always the case when we're dealing with general complex numbers in quantum mechanics. This is because the complex numbers can be different for each component of the vectors. They don't necessarily have to be the same as in your example. I see. Well, this is better. Okay, here we go. So it's just because I chose a wrong example here. This is why the general rule is that with the asterisk representing the complex conjugate, this rule guarantees that the equality holds in all cases, not just in specific examples. Okay, fine. Let's take the conjugate then. Let's do that. So I'm going to go to 8 here, and now we're getting somewhere, right? Because now I understand. Ah, it's just a flaw in my example. Okay, well, happy days. So let's go to here, and I shall say, okay, let's take the conjugate. So the conjugate, so PV equals 8 plus 8i, 8 plus 8i, 2 plus 2i, 2 plus 2i is equal to 8 plus 8i, 2 plus 2i, plus 8 plus 8i, 2 plus 2i, which equals 16. This reminds me of in Friends where it's like, oh no, is it Friends? No. 2.5 Men where he's like flossing his teeth. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Exactly how I'm saying this now. 16 plus 16i plus 16i minus 16 equals 32. Alright, so we got that. Now let's take the conjugate. So VP conjugate is equal to, I have to draw this nicely because I'm going to get myself confused here. It's going to be 8 minus 8i, 8 minus 8i, 2 minus 2i, 2 minus 2i, which equals 8 times 2 is 16, minus 8 times minus 8i is 16 minus 16i. 8 times 8 times hang on, sorry. Hang on. It's 16 times 8 times 2 is 16. 8. Oh, what am I doing? Let's just write this out. Um, it's going to be 8 minus 8i times 2 minus 2i plus exactly the same. Copy. How do I paste this? Oh, alright, well I just write out again. 8 minus 8i, 2 minus 2i equals, so you're going to have 8 times 2 is 16, and then 8 times minus 2 is minus 16i, and then 8 8i times 2 minus 8i times 2 is minus 16i, minus 8i times minus 2i. Ah, here we go. It's going to be um, minus 8. So 8 times 2 is 16, minus 16 times minus 1, minus 16 times minus 1, minus 16 times minus 1, minus 16 times minus 1 equals 16. So plus 16. Okay, so which equals 16 plus 16 is 32. Minus 16i minus 16i is minus 32i. This is 16, this is 32i. 32i. Yeah. Oh dear, because they're different. Okay, well, let's let's do this then. Let's now introduce the correct way. We already know that, and now let's take the conjugate. VP conjugate equals 8 minus 8i, 8 minus 8i, 2 minus 2i, 2 minus 2i. Happy so far? Shall I carry on? For inner products of vectors PV, where P and V are vectors, if P equals P1, P2, and V equals, then the inner product is defined as P1 conjugate V1 conjugate plus, where the star denotes the complex conjugate, yep. So if you want to compute V, it's not the vectors that are conjugated, but the results of the inner products. Eh? Let's take P equals plus 8i and V equals, yeah, as in your example, we already know that P vector is 32. To get VP, you'd first calculate VP without the conjugate, then you take the complex conjugate of the result, which is minus 32i. This is what we mean when we say VP equals, we're not conjugating the vectors themselves, but the result. So it's true that PV equals VP for this rule is general and holds for all complex vectors, not just, but 32i does not equal minus 32i. How can how can the complex conjugate of a pure imaginary number such as 32i is its negation. However, in the context of the inner product, we should be taking the conjugate of each component of the vector before multiplying, not of the final result. Let's do it correctly. PV is calculated as 8i, 2i plus 32 plus 2, 64. Yeah, okay, fine. Yep. I just made a mistake here, that's fine. Um, wait. 8i. No. So far it looks like PV equals, as in your original claim. However, if we consider the complex conjugate rule, the inner product should be computed as 2 plus 2i, okay, fine. Right, okay, let's use that then. So say it's 2 plus 2i. Of course. No, what? Wait, no. So far it looks like PV. However, if we consider the complex conjugate rule, the inner product should be computed as equals 64 minus 64i. Now we see that VP does not, rather, VP equals where the star denotes the complex conjugate. I apologize for the. This doesn't make any sense. Yeah, I'm totally confused. Let's come back to this. This isn't working for me. Okay. So thanks for coming along. If you come along, 4 hours 11 minutes. Yeah, I need a break.